nearly 2,000 miles beneath your feet, past the crust, past the mantle, at a boundary where solid rock gives way to a churning ocean of molten iron. Something has been changing that scientists have spent decades trying to prove was even possible. For most of modern geology, the deep interior of Earth was treated as the one part of the planet that didn't behave unpredictably. The surface could shift, erupt, and shake. The deep Earth was supposed to be different. Slow, stable, operating on timescales of millions of years. New data pulled from seismic instruments positioned around the globe has just confirmed something that upends that assumption entirely, and the researchers behind it are being unusually direct about how significant it is. To understand why this discovery has seismologists abandoning their normal caution, you first need to understand what they were actually looking at. Earth's inner core, that solid iron ball sitting at the very center of the planet, roughly the size of the moon, isn't fixed in place the way most people imagine. It floats inside the liquid outer core, and for years, researchers have debated exactly how it moves relative to the rest of the planet. Some studies suggested it rotates slightly faster than the Earth's surface. Others argued it lags behind. The debate has run for the better part of 2 decades, with each new paper seeming to contradict the last, because the tool scientists use to see that deep. Earthquake waves passing through the planet only gives them scattered snapshots, not a continuous video. What changed is the data set. Researchers assembled decades of seismic recordings from earthquakes that occurred in nearly identical locations, sometimes decades apart, essentially creating repeated scans of the same slice of deep Earth taken at different points in time. When waves from these matched earthquake pairs were compared, the timing differences were unmistakable. The inner core's rotation relative to the mantle isn't just variable. It has recently reversed direction. For years, it appeared to be spinning slightly faster than the rest of the planet. The new data shows that trend has stalled and is now moving the other way, slipping slightly behind the mantle's rotation instead of ahead of it. That might sound like a technical footnote, the kind of finding that stays contained to academic journals. It isn't. This is the first time researchers have been able to confirm, using this kind of matched pair seismic evidence, that the inner core doesn't just spin at a different rate than the rest of the planet. It periodically changes which direction that difference runs. And that matters because the inner core's behavior isn't isolated from everything happening above it. The churning of the liquid outer core around that solid inner ball is what generates Earth's magnetic field, the same field that shields the entire planet from solar radiation and makes life on the surface possible in the first place. Changes in how the inner core rotates relative to the outer core can influence the flow patterns in that liquid iron ocean, and flow patterns in that liquid iron ocean are the engine behind the planet's magnetic field. Researchers are careful here, and this is important. Nobody is saying Earth's magnetic field is about to collapse or that a pole reversal is imminent. Those are separate, much longer processes that scientists monitor through entirely different lines of evidence. What they are saying is that this newly confirmed shift adds a data point that reshapes the models used to understand how the inner core, outer core, and magnetic field interact over time. Models that inform everything from how scientists interpret ancient magnetic field records in rock formations to how they predict long-term changes in field strength going forward. There's also a length of day angle to this story that connects the deep interior of the planet to something almost absurdly ordinary: the length of a single day. Because the inner core and the rest of the planet are gravitationally and magnetically coupled, changes in how fast the inner core spins relative to the mantle can produce tiny, measurable shifts in Earth's overall rotation speed, changes on the order of milliseconds. Precision timekeeping systems, the kind that underpin GPS satellites, international financial trading networks, and telecommunications infrastructure, depend on Earth's rotation being accounted for with extraordinary accuracy. Scientists have already noted unusual small variations in day length correlating with the timing of this inner core shift, variations too small for anyone to notice in daily life, but large enough that the institutions responsible for global timekeeping standards take them seriously. What's driving the reversal itself is where the research gets genuinely uncertain, and where scientists are the most cautious about overstating what they know. The leading explanation involves the gravitational pull of the mantle acting on the inner core, along with the churning dynamics of the liquid outer core surrounding it, creating a kind of long-period oscillation, the inner core speeding up relative to the mantle for a stretch of years, then slowing and reversing over and over on a cycle that may span several decades. If that explanation holds, this wouldn't be a one-time anomaly. It would mean the inner core has likely been oscillating back and forth like this for a very long time, and scientists are only now, with a long enough data set and matched earthquake pairs precise enough, able to actually see the pattern clearly instead of catching contradictory snapshots of it. That reframe matters because it changes what kind of discovery this actually is. It's not a warning about an imminent, catastrophic shift happening deep in the planet. It's confirmation that Earth's interior operates on a rhythm scientists didn't have the tools to detect until now, a rhythm that ties directly into the systems that protect the surface of the planet and quietly keep global infrastructure synchronized. The unsettling part isn't that something dangerous is happening. It's the realization of how much about the deep Earth, a place that shapes conditions on the surface in ways most people never think about, remained essentially invisible until researchers found a way to look at it correctly. For the scientific community, this confirmed reversal opens up a new set of questions that will likely dominate deep Earth research for years. If the inner core genuinely oscillates on a multi-decade cycle, what sets that cycle's length, and has it been stable throughout Earth's history, or is it itself changing? How tightly coupled is this rotational behavior to fluctuations already observed in the strength and shape of the magnetic field at the surface? And perhaps most pressingly, for anyone building systems that depend on precise timekeeping, how predictable are the length of day variations this produces, and do current models need to be revised to account for them going forward? Seismologists are already working to extend the matched earthquake pair method further back in time and to new regions of the globe, hoping to map the oscillation with enough precision to eventually forecast its next turn, rather than simply confirming it after the fact. That's the shift happening right now in this field. Moving from a decades-long argument about whether the inner core's relative rotation even changes direction, to a new era of trying to understand the mechanism well enough to predict it. For a part of the planet that sits under nearly 2,000 miles of solid rock and molten iron, completely inaccessible to direct observation, that's a remarkable turn, and one most people watching the surface of the Earth every day will never realize is unfolding directly beneath them. To really grasp how remarkable this confirmation is, it helps to go back to how scientists even found out Earth has a solid inner core in the first place. It wasn't until 1936 that a Danish seismologist, working through earthquake records by hand, noticed something odd. Seismic waves passing through the very center of the planet were behaving differently than the models of the time predicted, arriving faster than they should if the entire core were liquid. Her conclusion, radical for the era, was that there had to be a solid sphere sitting inside the molten outer core. It took decades for the wider scientific community to fully accept it, because there was no way to see it, no way to touch it, no way to sample it. Every single thing scientists know about the inner core has been reconstructed indirectly, through the behavior of waves that pass through it and come out the other side changed. That's the tradition this new discovery belongs to, and it's worth sitting with, because it means researchers are still, nearly a century later, mapping one of the most consequential parts of our own planet almost entirely through inference. That indirect method is also exactly why the rotation debate dragged on as long as it did. Earthquakes don't occur on a convenient schedule, in convenient locations, at a strength strong enough to send readable waves cleanly through the inner core to a seismic station on the opposite side of the planet. Researchers have had to wait, sometimes for years, for two earthquakes to occur close enough to the same location that the wave paths through the core would be nearly identical, giving them something genuinely comparable. Early studies were working with a handful of these matched pairs, which is part of why results kept contradicting each other. A handful of data points from a system that might be oscillating over decades is like trying to understand a pendulum's full swing by only ever glancing at it twice. You might catch it moving right in one glance and left in another, with no way of knowing if you're watching one slow arc or two entirely separate movements. It's only with the accumulation of many more matched pairs, spanning a much longer stretch of time, that the actual shape of the motion started to emerge clearly enough to confirm a genuine reversal rather than noise. The research team behind this confirmation didn't just rely on one earthquake source either. They cross-referenced results from multiple seismic zones, comparing the pattern detected in waves passing beneath one part of the globe against the pattern detected beneath entirely different regions, to make sure they weren't looking at some kind of local anomaly in the data rather than a genuine planet-wide signal. When the same underlying pattern showed up across independently analyzed regions, that's what pushed this from an interesting hypothesis into something the broader seismology community is now treating as settled, at least in terms of the observation itself. The interpretation of what causes it remains open, but the fact that it's happening is no longer seriously in dispute among the researchers who specialize in this exact question. It's also worth putting this discovery next to what scientists know and don't know about other rocky planets in our solar system, because it reframes how unusual Earth's setup actually is. Mars, for instance, appears to have lost its global magnetic field billions of years ago, and the leading explanation is that its core cooled and solidified in a way that stopped the internal churning that generates a magnetic field in the first place. Without that shield, solar radiation is thought to have gradually stripped away much of the Martian atmosphere over deep time. Earth's core, by contrast, is still active, still churning, still generating the field that makes the planet habitable the way it is. This newly confirmed oscillation in how the inner core rotates isn't a sign that Earth is somehow following a similar path toward losing its field. If anything, it's evidence of just how dynamic and alive Earth's interior still is, compared to a planet like Mars where that internal engine effectively switched off. But it does underline how directly tied the surface conditions we take for granted are to processes happening thousands of miles down, completely out of sight. Reactions from geophysicists outside the original research team have been a mix of genuine excitement and the kind of careful, technical scrutiny that's normal for a finding this significant. Independent researchers have pointed out that this result, if it holds up under further testing, effectively closes one of the longest-running open questions in solid Earth geophysics, while immediately opening several new ones in its place, which is generally treated as a good sign in science rather than a bad one. Fields that stop generating new questions are fields that have stopped being interesting. Several teams not involved in the original study have already announced plans to independently reanalyze the same matched earthquake pair method using their own seismic archives, specifically to see if they can replicate the reversal signal using data the original team didn't have access to. That replication effort, still ongoing as this video is being made, is exactly the kind of scrutiny a finding like this needs before it becomes fully accepted textbook material rather than a single team's interpretation. There's a public misconception worth clearing up directly, because headlines about the Earth's core doing anything unexpected tend to get stretched into something scarier than what's actually being described. This isn't the same category of finding as a pole reversal, which is a much slower process involving the magnetic field itself, flipping polarity over the course of many centuries to millennia, something Earth has done many times in its geological history without catastrophic consequences for life on the surface. It's also not related to core collapse, core cooling crises, or anything that would threaten the magnetic field's basic function of shielding the planet. What's been confirmed here is a change in relative rotational direction between two layers of the planet's interior, a subtle mechanical behavior, not a structural failure or a sign that anything is breaking down. Scientists studying this are emphatic on that point, precisely because they know how easily a phrase like major change deep beneath Earth's surface can be misread as an early sign of something disastrous, when what it actually represents is a long-hidden natural rhythm finally being measured accurately for the first time. That said, the practical implications researchers are tracking are real, even if they're not catastrophic. Beyond the length of day variations already mentioned, some geophysicists are examining whether this oscillation pattern correlates with the subtle, well-documented wandering of Earth's magnetic North Pole, which has been drifting at an accelerating rate over the past few decades, enough that international standards bodies have had to update navigational models more frequently than in the past to keep compasses, ship navigation systems, and some military and civilian positioning technologies accurate. Nobody is claiming the inner core's rotation directly causes that polar drift. The relationship, if it exists at all, is likely far more complex and indirect, but it's exactly the kind of question this new dataset gives scientists the tools to finally start investigating with real evidence instead of speculation. What makes this moment particularly interesting for anyone following Earth science closely is the sense of a long-standing mystery finally yielding, not through a single dramatic breakthrough, but through the patient accumulation of decades of data until the picture became undeniable. That's rarely how these discoveries get portrayed once they reach headlines, but it's almost always how they actually happen. Seismologists didn't wake up one day and detect a reversal. They spent 20 years slowly building a dataset precise enough and long enough to finally separate genuine signal from decades of conflicting noise. The confirmation itself is the payoff of that patience, and it's part of why researchers in the field are treating it with the kind of quiet, focused seriousness usually reserved for findings that reshape a discipline rather than just adding one more headline to it.